I hope all of you can hear me.
Yes, sir.
Right. So still I see only 14 participants, including me, which means there are only 13 students. And it's 6:10 almost. Yeah. So shall we start the session? I don't know whether others would join or not. Okay, let's start. For better experience, I mean, I know that the internet is not that good over over the entire country, so there might be uh, streaming difficulties. So I will switch off my camera, so that will help some of you to have better experience with this uh, lecture. Right. So let me start the session, and this is the first lecture that we conduct in this course, uh, database security. And today it's the introduction, and we will do follow these topics throughout the course. Database views as a security tool, and then we will be looking at database authentication and access control and SQL injections, also auditing and encryption if possible. And we will be specifically looking at cloud uh, security implications in the context of cloud databases, as well as NoSQL databases. So those are the things that we would follow throughout this course. Um, Assessment plan for or the evaluation plan for this course is 40% from the uh, assessments. Mainly they will be in-class assessments, and also we will have final examination at the end of the semester, so that will contribute 60% of your score. So I have shared all the links for these Zoom sessions here. You will be able to click this link in the VLE page and go to all the Zoom session links. So please join with the right Zoom session, so you will be able to join with this lecture. Okay, if we look at the evolution of databases, right? So databases are mainly for our record keeping, or storing the data, right? So throughout the history, we have this requirement of keeping or the storing the data. So if we look back earlier, we had manual file systems where no computerization was there. So even before the computer was invented, record keeping was a necessity. So people use manual file systems where the data is stored and maintained in paperwork, right? Papers. We using physical documents, and it required a lot of human effort. Uh, so that period we didn't have these computers. Then with the arrival of computers, people people got this requirement of having data in computers, so they started with flat file systems. So flat file systems basically data in a single simple text file or single file without any association or any link between uh, data. So there were no relationships. That's the easiest way to start this record keeping. We know that when we want to store or keep a small piece of information, we just open a notepad or maybe a note in a computer. So we keep that information in that particular notebook or whatever the application. So when the information that we have to store is smaller, not in larger quantities that we can manage with a flat or maybe a single text file. But when the amount of data grows, it's really difficult to manage things in a single file. I know that you all experience this when the file size or maybe the content grows, it's really difficult to search things in a single file or else track them or maybe finding out changes or maybe finding right position to insert new stuff. So those are things that we find it difficult with flat or a single file. Then it comes hierarchical databases. So hierarchical, it's like a tree-like structures where parent-child relationships are maintained. So data entities can have many childs, children. Uh, However, a child data record can have only single parent. So that is how the initial level of relationships among the data was introduced, or the requirement of relationships among data was addressed. So they initially proposed tree-like structures. So time being, they understood, I mean, the people or the researchers, scientists, they understood this is not going to work. So parent-child relationship does not always ensure the required data representation and the efficiency and the ease of use. So there is a major limitation where that a child record can have only one relationship, one parent, and parents can have many children. So it's like one to many relationship in between them. So there are instances where we have more many to many relationships should be maintained. So likewise, there were certain other limitations with hierarchical DBs as well. Then it comes network databases. So network here does not mean the physical networks. So or the data communication networks. This is just to give the idea that the data records are represented as a network of records. So the data is organized as a graph. So many to many relationships, one to many relationships, and all these things can be represented. However, again, there are certain inconsistencies, inefficiencies encountered with the network database models. So that's why more efficient, more consistent and reliable data representation model, relational databases were introduced. So the relational databases gives the idea of keeping information in a sort of relation in mathematics. So it's basically based on relations in mathematics. So that's why it is called relational databases. So relations to store data and allows complex querying with SQL. So that is the core concept of relational databases, and it has been proved that this relational databases model is so robust in representing all these data model and data requirements, and uh, strong enough to sustain these all requirements that we experience throughout the development of computing technologies. So even today, we see that relational database model is somewhat prominent and priority. Thereafter, some models were introduced like object-oriented databases. So you know that there is a software engineering context, uh, programming paradigm was introduced lately. That is object-oriented programming. So object-oriented programming, when we do programming with object-oriented way, we want to keep data in storages as well. So that requirement exists in different whatever the programming paradigm we follow, our data uh, saving or the storage requirement exists. So object-oriented databases were invented or introduced to work with these programs where, or the software systems where they were developed using object-oriented program development. So it can directly engage with object-oriented databases. So it looks more compliant. Uh, so it was, even though it was introduced after relational database models, it could not surpass, or maybe could not extend the limits of relational database, or the popularity of relational databases were not affected. So uh, still relational databases work well. And thereafter, NoSQL systems, NoSQL databases came to uh, popularity, and cloud databases, and that is how the evolution of database systems uh, we see throughout the history. So a database is basically uh, uh, a systematic storage that facilitates efficient and effective use of data. So in this regard, there can be lots of requirements facilitating efficient and effective use of data. It's not just about simply storing data. We want to store the data as well as we want to search data. We want to update existing data, and we want to delete data. We want to modify, and we want to add new data for existing models. So there are lots of requirements that we need to manage with this efficient and effective use of data. And also we see that widespread applications, which means database is an essential element of current world information system. Uh, it plays a major role in any system. I mean, all the business organizations, all the other organizations, they require these databases for their information systems. Also, there are different varieties of databases. Like centralized databases and distributed databases, cloud databases. And if you look at the data model, again, we will see that relational databases, SQL, no SQL databases, likewise, quite diverse area right now. So here the data is an asset. So when we keep information or when we store this data, it's an asset. So we know that in the modern world, data is the most precious thing. All the uh, top tech companies, all the leading companies in modern world, they are working with data. So the value of data is unbelievable right now. With the advent of AI technologies, the importance of data has been increased a lot. So when it becomes an asset, so it forces, it brings lots of um, risks as well. So asset is always an risk. So if you look at different levels of sensitivity, so we know that there are lots of uh, sensitivity levels with regard to this data. Some data can be exposed publicly. Doesn't matter whoever has the access to it, but some information, the level of sensitivity is restricted and some are very confidential. As I said earlier, uh, databases or database plays a fundamental or very important role in modern information systems across various industries and sectors. Uh, importance the importance of these databases originated from their ability to efficiently store uh, and manage these large amounts of data. So we need to store the data, retrieve, manipulate, and lots of different ways that we can manage this data. So if we look at the role of the databases in modern context, first thing is basically uh, the data storage requirement. So it's mainly a storage uh, mechanism. But we know that in the modern context, the role of the database go beyond the basic requirements of data storage. So it right now it requires or it demands lots of other features as well. So as the first role, it's a storage medium or the storage mechanism. So databases provide a structured and organized way to store large amounts of data. So they offer mechanisms for uh, defining the data schemas, structures, or if it comes to relational database tables, and defining. So databases provide mechanisms to define relationships among data, and also while doing all these storage and definitions, data storage requires integrity and consistency. So those are important aspects of data storage. Second, data retrieval and query is another important aspect for the role. So databases allow users to retrieve specific data or maybe subset of data. So it may provide querying mechanisms and other ways, query languages. So it ensures that you can efficiently access to relevant information and facilitate decision making and analysis. And if we look at data integrity, so databases implement features to maintain data integrity, such as constraints, transaction-related integrity mechanisms, and also access controls. So these mechanisms ensure that data remains accurate, consistent, and reliable. So concurrency control is another important aspect or the role that modern databases play. That is when we are dealing with or when we are serving multiple users in quite diverse requirements. So the database must handle all these diverse requests from the clients, right? So the database need to manage this concurrent access by the users or applications. So concurrency control mechanisms are required in modern database management systems. So such as locking and transaction isolation, ensuring data is reliable and accurate, and avoiding corruption. So all these are part of concurrency control. So that is another role that modern databases play. And also scalability and performance, that is an aspect that modern databases really paying the attention, because it is catering for large amounts of users or the clients. Right now it handles large amounts of data day by day. The amount of data increases, so there are scalability and performance issues. So modern databases should be able to scale both vertically and horizontally. So this scalability enables systems to handle increasing data volumes, and clients it can maintain performance levels it demand. Then apart from that, data analysis and reporting is an essential component, and also integration with applications, which means we may need to integrate our databases, or maybe various applications need to integrate with databases, systems, and interoperability between different components of an information system. Sometimes we may need to connect with web applications. Sometimes we may need to interact with mobile applications. So all these diverse integrations are required. And also data backup and recovery. So you know that data backup is an important attribute these days, because in a disaster, data backups are really important. We never know at which point we might experience such a disaster, so it's better to prepare them well. Uh, uh, so databases provide mechanisms for backing up data and restoring it in the event of data losses or corruption. And also compliance and governance is another area that modern databases facilitate. Databases support compliance with regulatory requirements and industry standards. So you know that there are laws and standards related to data privacy, security, and governance. So these databases now should support these compliance and regulatory requirements. So features such as auditing and encryption, access control. Those features help organizations to enforce their policies and adhering to standards and compliance requirement. So the complexity in the modern context, why it is complex? Because you know that it's technological advancement mainly, so it's not that simple database. Now we have it's very complicated, complex data access environments have been uh, established. So people, I mean, large amounts of data is being processed, large amount of clients are connecting, and it's over the network, and sometimes these data storages are distributed, sometimes we might be in cloud environment. So technological advancements have already made these data environments complex. And at the same time, the bad guys, so they have advanced their approaches as well. So advanced intrusions are always uh, inevitable. So we have to be prepared them as well. So in summary, what we can do is we can only manage these risks. So we have to understand the total risk we have and ensuring the sufficient level of controls so we can manage these risks. That's only we can do. We cannot ensure that 100% security. So it is impossible to achieve. So only what we can do is managing these risks in proper way. So security requirement, why we are really bothered about the requirement of security. So there can be accidental losses and accidental corruptions of data. At the same time, unauthorized parties may attempt to access the data and perhaps alter it. So that is the major concern, and also undue delays in authorized access in a scenario such as denial of service attacks and refute of action or misuse. Sometimes parties might refuse or refute that they have committed something. So in that case, we need to maintain proper access records to ensure that their access histories are maintained. Common threats and vulnerabilities. Uh, Basically, these are quite common list of threats and vulnerabilities. So unauthorized access and data breaches, basically unauthorized parties, individuals gain unauthorized entry to the database system or data. So unauthorized access or disclosure of sensitive or confidential data stored in databases. These incidences can occur due to various factors like uh, weak security controls or maybe weak authentication mechanisms, improper access control, maybe insider or malware. So different reasons might be there. And also SQL injections. So that is another uh, threat type. So people may pass a script or part of a script to the database through a user application and breach the security controls and weak authentication authorization and insecure configuration, which means uh, in, uh, improper configuration of database servers and the utility services, applications, or maybe network infrastructure. So all these things may expose databases to various vulnerabilities. You know that in any information security requirement that we may look at several objectives in information security. You may have already um, heard this, right? Security objectives in any context. So those are basically confidentiality, availability, integrity, and sometimes we highlight non-repudiation as well. So when it comes to a data environment, what it means as confidentiality is data must only be available to intended parties. So non-intended parties should not access the data. So the confidentiality is basically we are releasing or we are sharing the data only with the intended party. So others should not be able to access this. So that is the confidentiality aspect of uh, data in databases. Second, availability. So what it means availability in data environment is data must remain accessible to intended parties. So it should be available for everybody who are intended to access it. So intended parties should not be prohibited from accessing data. Third is data must remain consistent, trustworthy, and accurate. Data must remain consistent, trustworthy, and accurate. So that is what it means integrity. And finally, non-repudiation is nobody should be able to refute an action that has been performed or that has been committed. So if someone says or can refuse a performed action or activity, that's a major problem. So the system, database system, should be able to deny this. Non-repudiation means nobody should be able to deny or refute an action that he or she has been performed. Another two important aspects of data is consistency and reliability, right? Consistency and integrity. So those two aspects mainly contribute to the reliability of data. So consistency is mainly about uh, maintaining the right representation among multiple instances. So these multiple instances does not necessarily mean that multiple copies. It can be over the period of time as well. So from one state to another, right? So it should properly represented identical representation of multiple instances of the same data. So integrity is basically it assures the accuracy and consistency of the data over a period of time. So that is what mainly define these terms. So if we look at consistency focuses on maintaining the internal logical rules, structures, constraints of data within a single database transaction. So it is about having uh, right representation or the correct representation uh, from one point to another. So it ensures that data changes do not violate predefined rules or relationships. For an example, if a database has a constraint that ensures the product's price cannot be negative, so data consistency ensures that any update to the product's price adheres to this rule. So that is what mainly consistency is about. Next, integrity. Integrity encompasses a broader scope, covering not only the internal rules within a single transaction, but also long-term reliability and correctness of data. It ensures data remains accurate and consistent across various operations and interactions. As a summary, we can say that consistency is a subset of integrity. So that is a rough idea about consistency and integrity. So consistency is like a subset of integrity. So consistency mainly focused on the validity of a transaction, while integrity is the overall health of data. So that is a little bit about consistency and integrity. However, sometimes these two terms are interchangeably used by uh, the professionals in this domain. So it's no clear-cut usage uh, standard for these two terms. But mainly consistency is about uh, the validity of a transaction. So from a single transaction's point of view, it should ensure the accuracy of the data, and the integrity is not just about a single transaction, it's about the overall uh, correctness of the data to a longer period of time. So secure data environment is basically against these theft, alterations, misuse, any other activities, intrusions, and attacks. So we should have a shield against all these negative impacts. So as the shield or as the mechanism against these negative stuff, we should come up with uh, procedures, standard policies, and tools. So that's what we can uh, establish, or that's what we can propose against this negative stuff, right? So database security is about establishing these procedures, standards, policies, and tools. Uh, so it will help us to protect data from these things, theft, misuses, alterations, and all these things. For database security, mainly with the use of database software. So database management system, right now it's a software package. So it's not just facilitating storing the data. So it facilitates securing this data as well. So mainly database security relies with database application system. Um, we will be looking at permission and access control to operations, data structures, data objects, and data. So that is how the database security is enforced. So in this regard, right, so making database a secure environment, we say that we are approaching a defense in-depth approach. So the key idea or the main idea in defense in-depth is to make a series of obstacles for unintended users, right? So it's accessing data. Accessing data is a long journey if we look at uh, the broader picture of this connectivity. So the user accessing data means the user go through different channels, different devices, different paths in order to reach the data. So if we can enforce different controls, or maybe if we can force different challenges, obstacles for unintended users in different points, So that will be making unintended users uh, life. It makes their life difficult, right? So they will not be able to achieve their objectives easily. So that is a way, or there is an approach that we can take when we are going to secure the data environment. So it's basically not relying on a single security mechanism, right? Instead, uh, approaching this securing this environment in multiple levels. So we can bring different controls at different levels in this journey. And for an example, again, if we look at the authentication level, we can go with multi-factor authentication at user level, and at the endpoint detection and response, right, at the PC level. And then the network level, we can go with firewall, um, and then at app server level and web server level, we can go with firewalls. And in the database level, we can go with encryption. So there are wide variety of activities or wide variety of challenges we can pose for the unintended user. So this will avoid single point of failure where bad guys will not have a single gate to open. So the same idea, the defense in depth, can be looked at another perspective, securing the data environment. So we can look at this entire story or entire requirement in a layered architecture, layered security architecture. So we can enforce different controls at different layers. So we identify three main layers here, but we can extend this model to many layers where it uh, nicely align with this defense in-depth approach. So to simplify things, we just look at three layers: uh, network layer, computer security layer, and then database security layer. So if if someone is going to access data, which means that the access requirement or the access request will go through this channel. So infiltrating these three layers, network, computer, and database security layers. So then if that is the intended user, then the intended user will be able to reach the intended data. But if that is an unintended user, that user should be denied at some point in this journey, at least in one layer. So that is the overall idea here in layered architecture. So this has been the most effective approach in minimizing the risk of data breaches, deploying multiple layers of security within database environment. So the network security is basically securing the network infrastructure, so we can bring the necessary hardware and software applications, with a few firewalls, intrusion detection system, proxy servers, and lots of other uh, hardware and software uh, utilities. Then the second level or the second layer, computer security, if the request reach and if the request go through or bypass the network layer, then it should be detected in the computer security layer. So this security requirement is mainly established uh, with the operating system. Security features are available within the operating system and can be expanded upon using third-party applications as well. So common computer security features include authentication, OS level authentication, OS level access control, uh, and application level security and hardware software monitoring logs, all these things. So these features vary by one operating system to another. So it's basically the vendor specific features. So the database layer, uh, it's the database itself. So the layer protects the database themselves. So measures that we can take is basically starting with access control and then encryption, data masking and redaction, auditing scenarios, vulnerability scanning, and also we can bring database firewalls. So those are specialized firewalls that monitor and control SQL traffic. And finally, backup and recovery features. So backups play a very important role in modern databases. A backup is a version copy of uh, data or the database. Uh, it's an intentional copy you take, right? So it can be about data or maybe program file or whatever. So it can be used to replace or restore your data and the system after a failure or maybe a disaster. So you need to have a right backup plan and backup management plan. So it will ensure the safety of the data and also the safety and the security of the backups as well. So when we are going for a backup solution for an organization, there are many things that we need to look at. Starting with what type of media should I use? So that is maybe one of the first things that we look at. What type of media should we use? Uh, one of the most, one of the first decisions that we take. Then there are different types of media available for backing up your data and choosing the right one for your business is the key, and it will depend on many aspects or many things such as the cost, compatibility with the your data environment and the labor and the potential for growth, things like that. Next, next thing is where are we going to keep this backup, or where is the backup to be placed? Backups should be saved in areas of the network other than the original data location. So it is to avoid both the original and the backup copy being destroyed in a single incident or the disaster. Backups should never rely on the same system as original data. It is not uncommon to move daily backups or the daily backup media offsite in order to ensure that it is not saved in the same place. And what should be backup, which means things to be backup, we have to identify uh, what are the data, to be backed up. So sometimes we don't need to back up everything. So in that case, we have to look at, or we have to identify what are the right things to be backed up. Backup frequency, which means how frequent that we are going to back up this thing. Then what time of day or night should be backup occur? Backup systems or backup process should occur during downtimes and the end of the workday, or things backup should not be completed while information is being saved or updated. So those are key things in backing up. Sometimes we have different types of backups as well, like full backup and partial backups, right? So it's important to identify the type of backups. So a full backup will back up all your information, uh, irrespective of its criticalness, right? So on the other side, there are incremental backups. So incremental backups are conducted uh, only the data that has changed since the last full or incremental backup will be backed up with this incremental backup. So as the incremental backup completes, it flags data that is being updated so that it is not included in the next incremental backup. So likewise, there are different types of backups. That disaster management, which is to ensure the restoration of system, network, and data. Uh, Business continuity is the most important thing for any organization. So if the disaster incident happens, uh, we have to ensure uh, we are running our systems normal in the event of this bad event with a minimum disturbance. Database management system, or DBMS in short, So it's the software application that facilitates storing, manipulation, retrieval of data. So we call this entire package, database management system, because it's not just a storage mechanism. It provides all these uh, auxiliary features as well. So if you look at database management systems, there are different types of database management systems based on the data model they follow. So at the beginning, I told you that there are different data models historically, how things evolved, starting with flat model. So there is a one model, and hierarchical model, another one, and a relational model, and object relational data model. So those are different models. So based on these different data models, NoSQL, right? So there are different database management systems. So we will be mainly looking at relational databases throughout this course, but we have several lectures on NoSQL data as well, uh, making sure that data environments are uh, sufficiently protected in NoSQL environments as well. So the relational data model or the relational databases are databases built on relational model. So why it is called relational? Because the underlying mechanism of this model uses relations, the concept of relation in mathematics, right? So so relations are mainly in more simple context, or in a way that we can understand in a simple way. We can think a relation as a table, but actually it's a mathematical concept where uh, it is described and defined with the help of set theory. So relations in this relational model is basically about keeping data in a tabular form. And also, this data is manipulated. The data stored in relational model manipulated with relational operators. So these operations are basically looked at or looked after as relational operations. So selection, projection, union, cross product, all these are the origins of these operators are in set theory, right? So there is a mathematical basis behind this relational model. So we are not going to uh, detail all of these mathematical aspects, but for your knowledge, just know that relational data model has a mathematical basis, and it's basically uh, relying on set theory. So the database schema is another term in this context. So database schema is how data is organized within a relational database. How data is organized within a relational database. So it includes logical constraints such as table names, fields, data types, and the relationships and all these things. So database schema and database instance are two different concepts. So if we take the concept database schema, it is considered as the blueprint of a database. So database schema describes how the data may relate to other tables or other data models. However, this database schema does not actually contain data. So that's why we call it's the blueprint, right? So it does not hold, or it's not about keeping data. So it does not contain data, but it's about how we are going to keep the data, right? So that's why we call it's the blueprint of database. So it describes how the data may relate to other tables and other data models. So the database name, table names, table fields, the data types, and the relationship among the entities, all these are about how we are going to keep this data. So that is what defines database schema. So the other term is database instance. It is about, or we can say, it is a sample of data from a database at a single moment in time. So that is what we call database instance, a sample data from a database at a single moment in the time, right? So from one instance to another, the containing data might be different, right? So that's why we call it database instance. It has a temporal aspect, at which point what we are referring in this data, right? So it contains all the properties that the schema describes, right? So it should, the instance, database instance will follow and adhere all the properties that the database schema describes, because database schema defines how the data may relate to other tables, and the data types, fields, and everything is defined in schema. So the database instance is, it is the sample of database in a single point. So database instance, they are likely to change constantly over time, because if you instant new data to a table, so now the instance is changed from the previous movement because it contains new data. But its schema has not been changed by inserting data, because schema is how it has been defined, but you are inserting new data. It does not change how you are going to organize them. Relational database objects, some of the key, commonly seen objects in relational databases. So you would see tables, views, and constraints, stored procedures and functions. Those are again database objects. Keys, indexes, sequences, and clusters. So the database schema is basically collection of all logical structures of data. or all the other objects. A schema is owned by a database user and has the same name as that user. So each user owns a single schema. Schema objects can be created and manipulated with SQL and include the following types of objects. Right, so I will mention here tables, right, views, uh, constraints, stored procedures and functions, right, uh, clusters, and there are many more uh, objects. And some of the popular database management system, relational database management systems. Oracle database, and then MySQL, uh, Microsoft SQL Server, and also PostgreSQL. So those are some of the popular uh, relational database management systems. There are product-specific configurations, controls, directives with respect to all these different relational database management systems. And also it can contain product-specific SQL syntax as well. So I hope you might have some idea about what is SQL, right? So SQL is, it's a abbreviation, right? So it's a short term. So it's about structured query language. So that is why we call it SQL. It's a domain-specific programming language. Basically, SQL is a programming language that you can use to interact with these databases. So you can query the database, you can use SQL for insert new data, for update, delete. So many different types of interactions can be done through using this SQL. SQL includes different types of commands. So there are different types of SQL commands that we can use to interact with the data database, and DDL, data definition language, data manipulation language, data query language, data control language, and transaction control language. So their definition language basically define and modify the structure of the database. So it's about you are creating the structure, or you are defining the overall organization of the database. Like, let's say you are creating a new table in the database. So you have to define it. So data definition language helps to define these things, defining columns, defining constraint, right? Next, data manipulation language. So it is about uh, data manipulation, right? Manipulating the data, like inserting new data or updating the existing data or deleting the data stored in the database. So these are what we call data manipulation, right? And then third is data query language. So query is basically retrieve data from the database according to our requirement. So sometimes we may have different requirement to extract data from the database. So there we can use these commands given in data query language. Data control language is basically control access to data within the database. So your access rights will be controlled using the data control language, mainly about SQL grant and revoke commands. So we will be looking at how these things work in data environment or the relational data environment. And transaction control language is about managing transactions within databases. So those are the main types of SQL commands, different types of SQL. Then I will just introduce the architecture or the overall architecture of Oracle database and Microsoft SQL Server, because those are the two most popular databases in the world. Other architectures, perhaps you can search by yourself. And when it comes to Oracle database specifically, there are two main components in their main server. So the first one is called database instance. So the database instance is basically the runtime environment of database, right? The runtime environment. It includes background process and structured memory used during interaction with the database. And all of these are in runtime, right? Runtime specification of the database. So the instance, the database instance manages the database memory, processes, user request, and coordinate access to data files. So this is about the database instance. And Oracle instance is it is the set of background processors and memory structures that operate on the database system or the data. It's what allows the database to function, or maybe users are, or the users clients are interacting with the database instance. So that is what we see in runtime, right? So users are connecting to the instance because we have to do everything when the database is in runtime, right? So here it's about the processes and memory structures that operates on database. The second component of the Oracle server is the database. So don't mix these two concepts up, right? Because you might be wondering, then we call Oracle database, then what is database and instance? So those are two terms which are used in Oracle context. So instance is what we see in runtime. So in runtime, we will see an instance of the database. So that is what we call database instance. So it includes background processes and structured memory used during the interactions with the database. So that is basically the instance. So then what is database? Database is the physical representation of the data, right? So it's files that an environment need to run the Oracle database. So these files help to configure the instance, made it possible for SQL execution to be processed and ensure alert and recovery from hardware and software failure. So it's basically the database refers to the collection of physical files on disk. So that store the data, metadata, and configuration related stuff. So it is the actual repository where data is stored and managed physically. So when it is in runtime, we call it instance. When it is in disk, we call it database, right? Uh, it includes data files, control files, and logs, right? Um, and those are the three main file types in Oracle context: data files, control files, and redo log files. Yeah, data file, it is the actual data and the relevant information to maintain the logical structure. Control file keeps the control information of other files such as file locations, credentials, and redo log file. This file contains information about all changes made to the data within the database. So this is somewhat similar to an undo button for the database, because this redo log can be used to restore data in an event that data is lost. So this is a diagrammatic representation of this Oracle database, right? So you may sometimes it might look complex. You don't need to entirely understand it, but it's good to have some kind of a understanding. So these are processes like clients and user processes. So these are clients and user. There can be many processes which are interacting and sending requests to the database management system or the database server. So in the database server, as I said in the previous slide, right, there can be database instance, right? So it is in the runtime, right? So we call it database instance. So processors and the user requests cannot be catered by the database which is not in the running mode, right? So if it is uh, physical storage, it cannot cater user requests, right? So it should be in running mode, right? So which we call runtime. So when the database is started, it will be initiating or initializing the database instance and running it. For each process, there will be a thread running in the or the task running within the database instance, right? So these tasks are representing the corresponding user process. And there are some key components in the runtime environment of the database instance. So this is called program global area, and this is called system global area, right? So by their names, you may perhaps understand or get an idea about what are the responsibilities of these two areas. program global area. So it's a private memory region for each database session or process. So you know that for each process, each session will be interacting with database as a separate session or the task. So this task will create process private memory region. So that is allocated within this program global area. So then to cater those tasks or the processors, you need some other facilities as well. Actually, the processing the data, presenting, structuring, and filtering all these tasks should be carried out in other areas in the memory. So that is basically system global area. It's a shared memory region that holds data and control information for efficient database operations. So it includes buffer cache uh, and other components like given here, right? So this is data buffer cache, redo log buffer, large pool, and some other components. And there is a shared pool, right? So all these processing related data and its related information in this system global area. So this is basically the instance, right? Database instance. So to run this instance, we need the physical files, right? So physical representation or the physical presence. This is where the physical presence is. So then we refer that physical presence as database. From the database, we will run an environment representing the data. So that is database instance. This is about system global area and program global area I mentioned earlier, right? These two. Then another key component in a database is data dictionary. The data dictionary is a collection of tables and views that stores metadata about the database, right? So we store data, right? So information systems need to store data. So those data will be stored in database tables, and there will be some other constraints that we create, right? Uh, Indexes, right? All these privileges, views, all these things will be created. So we need to maintain data about these data structures and things. So data about these data will be maintained in data dictionary. So that's why we call it the data dictionary. Is a collection of tables and views that stores metadata about the database. So the metadata is basically data about data. So if we say another way, the data dictionary is a centralized repository of information about data, right? So it's about data about or the information about data. So it provides detailed description of the data elements within a database or information system. For an example, let's say you create a database table for storing employee data. So then what you do is you will be interacting with this table and you will store data, employee data, you will delete, you will update, you will be interacting with this table. However, database management system needs to know what is this employee data, right? So it needs to know the name of this data, and it needs to know the column types, whether it's a number, it's a date, or it's a strings, right? So what are the types, data types, and what are the constraints, right? So all these columns, and whether there is a relationship between the table and another table. So all these supportive information about the data is stored in data dictionary. So it is an integral part of the database and is used by Oracle database management system itself. So it is not just for Oracle database management system. All the other database management systems also have this data dictionary facility, right? So core functions of data dictionary is metadata management. A data dictionary stores metadata, which is data about data. It describes the characteristics and properties of the data itself. And apart from that data definition, it defines the meaning, format, relationship, and usage of data elements. And consistency and standardization, it promotes consistency in data usage by providing a common reference point for data definition. So this is about MS SQL Server. Earlier we looked at Oracle. So if you carefully look at, again, it has these caches, right? Um, what else? Logs, right? So these are the physical files, right? Um, right. So, however, the way things are organized in MS SQL Server is a little bit different from SQL Oracle. Um, so they have first a protocol layer, and TDS is a application layer protocol to transfer data between client and MS SQL Server. So they have a application specific protocol which interact with their server and the client application. So that is what TDS. Um, so SNI here is, as I remember, this is called SQL or SQL Network Interface. That is why it is called network interface. So that is again an interface for client and the server. So then the request comes to relational engine. So there will be query optimizer, command parser, executor. So when there is a request come, so it's in SQL form, right? SQL. So SQL command or SQL query that comes from the client to the server. So this will use the parsing, which means it will check whether the syntax and all these uh, the commands are correctly written, properly written, and then it will optimize the SQL query, which is sent from the client, and then it will execute, right? And to support this relational engine, there is another component called storage engine, right? Storage engine, the responsibility is facilitating the relational engine to execute the command, but here there are transaction manager, access method, and buffer manager, lots of other components as well. So I'm not going to go into details because it's not that expected in this course to understand a very specific database server architecture. So two main components, the relational engine and the storage engine. Uh, Relational engine's primary responsibility is query processing and data retrieval. The task that the relational engine completes are initiated by user queries and include parsing the SQL, optimizing, and retrieving the results. So you see that this is relational engine. So it directly takes user request or the SQL queries from the user through this interface, right? The storage engine is for primary responsibility to ensure the effective management of memory, data, which is being processed, and files, recovery features, logging, and transaction management kind of things. So storage engine assures that memory is available and being allocated appropriately. Backing up is being completed as often as necessary, and all the supportive features are provided with this storage engine. So in the physical presence, there are three main file types in Microsoft SQL Server. First is primary data file. It is the main data file for SQL Server. So it mainly references all other secondary data files and is the file of origin for the entire database, right? So there will be single primary data file. So it is the point of origination. So it is the reference point, starting point for the entire database. Therefore, there must be minimum of one primary file with every installed database. Secondary data file, an optional data file found in SQL Server. So it is basically not the primary data file, it's a secondary file. Any data file that is not primary file is basically we refer it as a secondary file. Then log files, it is a file that stores information about the transactions in the database to be used for recovery and backup. So that will be a log. So some of the important features in memory management, SQL Server dynamically acquires memory. Virtual memory is because since SQL Server is by the Microsoft Inc., because they have also their own operating systems as well. So their database server may have, it has been optimized to run on Windows operating systems. So that's why it can dynamically work with memory and virtual memory support. So all these are compatible because Microsoft SQL Server runs on their own operating system, which is Microsoft Windows. Then we look at database transactions. A database transaction is a collection of actions or events that is regarded as a single logical unit of work, right? So some of you may already know what is a transaction, but for others' knowledge, you can perform different things with uh, atomic level SQL commands, right? You can insert the data to a table, or maybe you can delete something, right? But sometimes we want to perform a many or series of activities as a single um, operation within the database management system. So that is why we call it a collection of actions and events that is regarded as a single logical unit. So it should perform as a single logical unit. So it may contain a series of different actions, such as inserting data to one table and deleting something from another, updating something in another table. So likewise, there can be different activities, but it should be executed as a single logical unit, which means outside world should not see it as a series of activities. So the idea is we might have different actions like this. So the outside world should not see them as a series of actions. Instead, it should see this as a single unit. So it will start from here and end from here. So outsiders will see, okay, this has been completed and this is the result. So that is basically a transaction. So transactions in a database environment have two main purposes, right? So two main purposes here. The first one is to provide reliable units of work that allow correct recovery from failures and keep a database consistent even in case of a system failure, right? So if for an example, when execution of a transaction uh, unexpectedly stops, let's say it failed in the middle of the transaction, in which case many operations upon database remain uncompleted. So if it fails here, right, it might actually have failed somewhere here, right? At this point, some of the internal activities have been performed, right? But these activities should not be reflected as a result because the entire unit is failed now. So it should originally should go to the starting point here. It should not have these intermediate outcomes. Right? So that is why we call it to maintain consistency and integrity of a database. So that is the first purpose. And the second purpose is to run independent and isolated process concurrently. Right? Run independent and isolated process concurrently. Just imagine this is a single transaction. Similarly, there can be many other transactions running parallel, which means these transactions might have been initiated by different users or different clients. Now the database has received many transactions which should be executed concurrently. So in that case, all these transactions should be independent and isolated, which means uh, if this isolation does not happen, right? So isolation in the sense one transaction's internal impacts, internal order or internal results, intermediate results should not be visible to other transactions, right? So let's say there is a insert operation at the beginning. So until this entire transaction is completed, the data actually inserted in the at the beginning of this transaction should not be visible to the outside, right? So it should be isolated from others. So to provide isolation between programs accessing a database concurrently, that is the second uh, purpose. So if this isolation is not provided, the program's outcomes are possibly erroneous because another transaction which is running parallelly might be referring or using intermediate results, right? So that can affect the integrity and the consistency of the data. So that is why we call transaction management is very critical. So the transaction is a collection of actions that runs as a single logical unit, right? A series of activities which is running as a single unit, and it has two main purposes, which we call consistency and integrity, maintaining consistency and integrity, and running independent. So to ensure these purposes, right? So databases ensure or enforces four properties which we call ACID properties, right? So if a database management systems comply ACID properties, it supports transactions. A database management system that provides ACID properties is known as transactional database, right? So it supports transactions if and only if it ensures ACID properties. So let's see what are these ACID properties. So ACID A for atomic, C for consistent, I for isolated, D for durable. Let's see what is atomic means here first, right? Atomic is a transaction is a single unit, right? So either it succeeds completely or fails completely, right? As I described in the previous slide. So this is a transaction, and it may contain many list of actions, activities. So either this entire unit succeeds as a single unit or fails completely, right? So it means if it succeeds from here to here, you will see the results of this entire transaction, right? So this is the end, this is the start, right? At the starting point, database may have in a particular state. So the state may have been changed with this transaction. So you will change this change at the end, right? But if the transaction fails at the middle, somewhere here, it will fail completely, which means if it fails, it will go back to the initial state. So whatever you did here will not affect the state of the transaction. So that is why what is atomicity. So it succeeds completely or fails completely. If one of all constituent statement fails, then the entire transaction fails. So if one of these statements fails, the entire transaction will fail. That is the atomicity. Atomic. This is an atomic unit transaction. So we have to see it as a single unit. So if a database management system supports this property, it is supporting atomic property in the transactional databases. Then C, consistent. A transaction brings a database from one valid state to another valid state. So after completion, it will go from one valid state to another valid state. All constraints should be conformed before and after the transaction. So before and so this is where transaction happens. So before and this is before and this is after. So before and after, all the constraints that governs the data should be adhered, right? So transaction brings a database from one valid state to another valid state. So there cannot be any constraint violation or integrity issues at the end of transaction, right? So the state, it should be in proper state. Isolation ensures that concurrent execution of transactions leaves the database in the same state that would have been obtained if the transactions were executed sequentially, right? So what isolation means, when we are running several transactions concurrently, right? So this is T1, this is T2, this is T3, right? So I said that intermediate results within these transactions should not be visible to the outside, right? So this is a single logical unit. That is why we call it atomic. So when these transactions are running in the database concurrently, it should ensure that this concurrent execution of transactions leaves the database in the same state that would have been obtained if the transactions were executed sequentially, right? So after executing these three, it should come to a state, right? Let's say this is S2 and it comes from S1, right? So S1 is the state where we begin and then we run these three transactions concurrently. It comes to S2. this should be the same state as you executed T1, T2, T3 sequentially, one after the other, right? So if you run these three transactions not concurrently but sequentially, right? So if you run these three sequentially from this state, then it should come to the same state, right? So that guarantees these transactions are isolated, does not affect others even if they run concurrently, right? So that is an important property for being transactional. So incomplete transactions completely invisible. Finally, the D, as it D, durable, the effect of completed transactions is permanent. The effect of a completed transaction is permanent. Once the transaction has completed execution, the updates and modifications to the database are stored in and written to disk, and they persist even a system failure occurs after the transaction, right? So this is a transaction and there is a state S1 and it comes to S2 after execution. Let's say we come to this state and then there is a failure, right? So it doesn't matter if you restart the database, you will be able to come back to this state because the results of the transaction is permanent. The effect of a completed transaction is permanent, right? The result is available for other transactions to use after execution of a transaction. So those are the four properties. If the database management system supports this, it is called uh, transactional. So in other words, to be a transactional database, it must confirm all these four properties, right? So approach in achieving objectives, which means our security objectives to achieve, one thing that we need to do is risk minimization. We have to identify our risk and minimize it. Then the prevention aspect, that is the prevention. Risk minimization is we are planning for prevention. So we can enforce controls. The second approach is effective response, where if something happened, if something bad happens, then we have to detect it and effectively respond, right? So we have to continuously monitor it. So we call it that there won't be perfect secured system. There won't be 100% security, right? Therefore, every system tolerates security breaches to a certain extent. So we have to understand our level of tolerance, higher degree of assurance, higher degree of tolerance, right? Higher degree of assurance on security would affect the system performance. So that is the other side of this, right? So it's security will be having a cost, right? So it will be an overhead as well. So it is always a trade-off, right? So we have to identify the right balance. Security policy. So every organization has their security principles and they have their security philosophy. So organizational security policy is based on their requirement. So it detail their view on security requirement. So they will look at scope, breaches, and tolerance, assurance. So these are described and detailed there. Security policy, database perspective. Uh, we will look at system security policy, data security policy, user security. So lots of policies that we always looking at when we are into database security and related policies. So key questions that we ask uh, when it requires security in a data environment, right? So key questions, I mean, key questions in the sense, four main questions that we usually ask in uh, data environment, right? So those four questions are: who is this? Who can do what? Who can see it? And who did it? So those are the four main questions that we usually ask in a data environment. So who is this is basically knowing who the user is, who can do what is about, what are the things that a user can perform, what are the data that can be accessed, who can see it, and who can have the access, who are exposed, or the what data are exposed to users, which users, and then who did it. When something has happened, we want to know who has committed it, who has done it. So these four questions: who is this? Basically answered through the authentication, right? Authentication is to answer this question. Next, who can do what? What are the things that can be performed by different users? So that is about authorization. Who can see it? Basically encryption, right? Who can actually see the data? Finally, who did it? It is about auditing, right? So authentication and authorization, sometimes they mix it up. Uh, Authentication is the process of validating or verification the identity, and the authorization process is establishing mechanisms to control uh, access and actions and enforce limits that are linked to users' identities. So as the control measures, we mainly looking at uh, access control. So that is the main mechanism ensuring or enforcing security uh, requirement, right? Access control, which is basically selective or selectively allowing users to reach different parts of the database, right? So that is the main mechanism of ensuring the security. and then insurance control, flow control, and also data encryption. So in the coming weeks, we will be looking at how access control works and all the others are uh, enforced. Right, so that's about today's lesson. And if you have questions, we can discuss it now. Okay, if there are no questions, I will end the session. And thank you very much for joining.
Thank you, sir.